And I will share my screen. Okay. So class, can you see my screen? Can you hear my voice? Can I get your response?
Yes, Doctor.
Okay, thank you. So today we're going to start with chapter 3, analog modulation. So modulation, as we have learned previously in chapter 1, it is the process of changing the property of the carrier in accordance with the input variation. Okay. So modulation is a process of mixing. Okay. So you have to mix at least two input in order to produce one output. So if you see, if I draw my favorite picture again, so we have a transmitter, right? The transmitter. So the transmitter has an input signal, okay? Analog input signal, and we should add another input, which what we call it as the carrier, okay? The carrier. So the carrier signal also is an analog signal, which has a frequency higher than the input signal. Okay, so this is the input. Okay, and another one is a carrier. So carrier frequency would be higher than the input carrier. The carrier frequency would be much bigger compared to the input frequency. The input frequency, we name it as FM, frequency of the input message. Okay, so during the modulation, okay, so modulation needs at least two input. Okay, we need at least two input. One input message, another one is the carrier. Okay, so modulation is also a mixing process. So during the modulation, the carrier property will change in accordance with the input variation. And we have learned previously that there are three properties of the carrier that will change. The first one is the amplitude. Okay, so if the amplitude of the carrier change in accordance with the amplitude variation of the input signal, we call it as the AM signal, amplitude modulation, AM. Okay, so AM would be your project, okay, where you're gonna make a transmitter that can have at least two input. One is the carrier generated by the circuit, and another input is connected through your mobile phone, where you will always play the music, for example, from the YouTube. Okay, so you have the input signal from your mobile phone connected to your transmitter, and the transmitter itself will generate the carrier signal through the oscillator circuit in the transmitter. Then modulations happen. Okay, so if the amplitude of the carrier change, so we call it as the AM. But if the frequency of the carrier change in accordance with the amplitude variation of the input signal, then we call it as FM, frequency modulation. If the phase of the carrier change in accordance with the um, amplitude variation of the input, then we call it as PM. Okay, so for PM, the phase of the carrier change in accordance with the amplitude variation of the input. Okay, so this is the modulation process. And you also will learn about the demodulation process in the receiver. Okay, so we transmit the signal as analog. Okay, we receive the signal analog. Okay, and we're going to do the process analog and produce analog output. In the receiver later, you also will see that we will insert a carrier signal, okay, in the receiver to do the demodulation process in order to retrieve the original signal at the output. Okay, so chapter 3, basically we're going to learn these two main processes, the modulation and also the demodulation. And this is about the analog system. Okay, that means the input is analog and we transmit the signal as analog. Okay, so all processes happen as analog. Okay, so the topics covered in chapter 3, so we can divide into 5 subtopics. Okay, mathematical definition, the bandwidth modulation index, power calculation, AM modulator, and also AM demodulator. And for your project is about this one actually, for your project, AM modulator. So modulator is part of transmitter. Okay, modulator is a part of transmitter where it will do the process of modulation. Demodulator is part of receiver where it will do the process of demodulation to retrieve the original signal. Okay, then we move to part 2. Okay, for part 1 is AM, part 2 is angle modulation. So angle modulation is about FM and also PM, phase modulation. Okay, so angle is for both of these. Okay, you're going to see later that FM and PM are related to each other. Okay, they are related to each other, where I can say that it is like twin brothers, FM and PM. And we're going to have the same subtopic from subtopic number 1 until subtopic number 5, same as the above. Okay, so if we go to the introduction part, so the introduction part, as I said, that there are 3 properties which of the carrier which will change during the modulation process. The first one is the amplitude, and then the frequency and the phase. Okay, so if the amplitude of the carrier change in accordance with the amplitude variation of the input message, then we call it as amplitude modulation, AM signal. Okay, we're going to produce AM signal. But if the frequency of the carrier change in accordance with the amplitude variation of the input message, then we're going to produce an FM signal. Okay, frequency modulation signal at the output. If the phase of the carrier change in accordance with the amplitude variation of the input message, then we're going to produce a PM signal. Okay, phase modulation signal. Okay, so this is the introduction part. Okay, so modulation is the process of modifying the characteristic of input signal. Okay, sorry, modifying the characteristic of the carrier. Okay, so the characteristic of signal that will change is actually the carrier itself. Okay, not the input. Okay, the characteristic of the carrier change in accordance with the input. Okay, the input signal or the input message remains the same as usual. Okay, but during this modulation process, the carrier signal change. Okay, and the carrier frequency, as I mentioned, it is a high value of frequencies value compared to the input signal. Okay, carrier is using the radio frequency. Okay, what is radio frequency? Radio frequency is between a few kilohertz until a few gigahertz. Okay, for AM, the range of frequencies is between 576 until 1605 kilohertz, if I'm not mistaken, according to the standards. For FM, the radio frequency range is between 88 megahertz until 108 megahertz. So that's for the FM transmission. Okay. So AM, if we see here, AM is used for the many kinds of applications. Okay. So there are two-way radio mobile communications, for example, CB radio. AM AM also used in radio broadcasting, okay, and also for the TV broadcasting, which also used for the AM transmission, okay. So AM modulators are non-linear device. We need to have at least two input, okay, and we produce one output, okay. So what are the two input? It is the modulating signal and also the carrier signal. So in your lecture notes, you might see that the input signal is named as the modulating signal. So this is the input actually. Okay. So in your lecture note, you're going to see that modulating signal, message signal, modulation signal. So that one is actually referring to the input signal. Okay. So if we draw a simple diagram, for example, modulator. So modulator needs the input, okay, modulating signal, and also the carrier. Okay. So as I said that it needs at least two input. Okay, it needs at least two input and it produce one output. So I told you in chapter 1 that actually we can have many input. Okay, actually we can have many inputs and we can have one carrier, or we can also have many inputs and many carrier. Okay, but that one is for high level modulation techniques which use in the cellular mobile communications, for example the 4G communication, 5G, 6G, and so on. But for your syllabus, okay, for your syllabus, the limitation is only for one input message and one carrier only is enough for you. Okay. The rest you're going to learn in another subject for high level modulation technique. Okay. So the signal, so modulating signal will modulate the carrier, okay, and then it will be transmitted through the antenna as a radio frequency. The input signal, known as the modulating signal, so we assign with parameter VMT. Okay, VM is a function of time. Okay, VM function of time. So this is a function for the input signal, and for the carrier, the function is VC of t. VC function of time, where you're gonna see about this later. Okay. Okay. So there's equations for this. So there are several types of amplitude modulation. Okay. The most commonly used is a AM DSB-FC. Okay. AM double sideband full carrier. Okay. AM double sideband full carrier, or simply we use it as we name it as AM. Okay. So in your lecture notes, whenever you see AM, this is related to the double sideband full carrier. Okay, double sideband full carrier. Double sideband full carrier is the oldest AM signal. Okay, the oldest AM modulation signal. Okay, AM has a few family members. Okay, so there are other types of AM actually. Not only double sideband full carrier, we also have another type of AM signal. Okay, so the oldest is double sideband full carrier. I can say that the grandfather of AM, we call it as DSBFC. But the family member of AM, we have another types. For example, we have double sideband suppressed carrier. We also have double sideband reduced carrier. We have single sideband. And another one is vestigial sideband, VSB. So we're going to see all of this later. Okay. The first, we're going to learn about DSBFC. And for your project, it's up to you. You want to choose double sideband full carrier or suppressed carrier or single sideband and the others. Okay. You have the right to choose which one you like for your project. Okay. So AM, we can use the advantage of AM. It is a simple. It has a simple circuit. Okay. It is effective for transmissions. It is inexpensive. Okay, not expensive. AM used in the radio broadcast, TV broadcasting, aircraft, CB radio, computer modem, and etc. Okay, but there is some disadvantages of AM. Okay, so you see that this is AM. So this is actually referring to the double sideband full carrier. Okay, so now we are talking about double sideband full carrier. Okay, and double sideband full carrier also has disadvantages. Okay, one of it is it said that it is wasted of power in the carrier. Okay, so the carrier is not carrying any information, so it is considered as not efficient because it wastes a lot of power. And it wastes a lot of power even though during the ideal case. Okay, so you're going to see later about this issue. So this issue, both of these statements will be proved later when we learn about the AM power calculations. You're going to see later why the double sideband full carrier uh, will waste more power compared to the other types of AM. Okay, so both of these statements will be proved later why double sideband full carrier is wasted a lot of power. And double sideband full carrier also has large bandwidth size compared to the other types of AM, for example, single sideband. Okay, so this is there is advantage also related to the power, and another one the bandwidth. Okay, another one is the bandwidth. Okay, large bandwidth. So this is also a part of the advantage for for certain kind of applications. Okay, remember class, when we talk about advantage or disadvantage of AM, we might need to refer to a certain kind of applications. Some application doesn't care about the amount of power that you want to use. Okay, that means even though you use a high power for certain application, it is not a problem. But some other applications requires less power usage. So if the application needs less power usage, that means double sideband full carrier is not suitable. Okay, or if the application needs smaller bandwidth of transmitted signal, that means this double sideband full carrier is not suitable. Okay, so it depends on what kind of application that you want to use. Okay, and this is the basic block diagram of the modulator. So remember that modulator is a part of the transmitter. Okay, so again, my favorite picture. Okay, so within the transmitter, okay, within the transmitter, okay, so let's say I use a different color, for example. So within the transmitter, maybe somewhere here is the modulator parts. So modulator is somewhere here in the transmitter. And there are a few other processes. There are many other processes happens before the modulator and after the modulator. Okay, modulator is only a part of the transmitter. Okay, so we have the input message. Okay, VM. Okay, we have the input message, and we also have the carrier signal, which we're going to produce an output of AM signal at the output. Okay, and this is the equations. Okay, this is the general equations for AM. Okay, before that, can I get your response? Are you still there, students? Can you see my slide?
Yes, Doctor.
Yes. Okay, so please feel free to ask questions. Okay, you can interrupt me at any time. Okay, you can ask me question, or you want me to repeat again my explanation. I can do that, no problem. Okay, so if you see from these equations, don't be stressed. So this is a simple equation actually. So in ECS, in this subject, I think I can say that in terms of mathematics, you're going to see that this is a bit complicated. Only this part. The rest would be easy. Okay. So don't be scared of long equations like that. It's not long equation actually. It's a short equation actually. So I'm going to explain this one by one. Okay. And you need to understand this because you have to do the project for the AM transmitter, right? So this is important for you to understand about the signal that you want to produce, okay, by your transmitter. Okay, so as I mentioned that for modulation, we need at least two input, right? The one is the modulating signal or the input signal, okay? So we assign it as VMT. Okay, so VMT is a function of time. VM sine 2 pi FMT. VM is the peak amplitude, and this is the signal. And for the carrier, input carrier, we assign it as VCT. Okay, VC peak amplitude sine 2 pi FCT. So how does the signal looks like? Okay, so if I draw, make a simple drawing of sine wave. Okay, so maybe I am. So let's see like this. So if I draw a sine wave, so this is time versus voltage. Okay, so for example, VCT, for example, so the peak amplitude here, okay, the peak amplitude here is VC. Okay, similarly, the peak amplitude at the bottom here also minus VC. So capital VC is actually representing the peak amplitude. Similar with the VMT. So if you draw the sine wave of time versus voltage. So for sine wave, you see that the peak amplitude here is Vm. Okay, similar the peak amplitude at the negative side, this is negative Vm. Okay, so for your lecture notes, you see that the input is given a sine wave. Okay, you might wonder why we use a sine wave. Huh? So if you read in other literature books, Wayne Thomas's book, if you read Wayne Thomas's book, he used sine wave. But if you read other literature books, They might also use cosine, okay, cos, okay. So sine or cos doesn't matter, okay. It is a simple wave. But later, okay, class, when you do your project, your input is actually connected to another input sources, right? You can connect to your mobile phone. As I said previously, your transmitter can be connected to your mobile phone, right? Your mobile phone, if you play a song, okay, if you play a music from the YouTube, for example, the input is not a sine wave, okay? The input is not a sine wave. Even if you use a microphone as an input, your voice is not a sine wave. Okay, you can try it in the lab. Okay, check your voice. How does your voice looks like? Okay, if you have a microphone connected to the oscilloscope, then you can see how your voice looks like. Okay, I think now you can also check in the internet how does a voice waveform looks like. Okay, it is not a sine wave, it is not a cosine wave. Okay, so we use a sine wave because it is a simple, the most simple signal. Okay, it is a repetitive wave. Sine wave is a repetitive wave, and it is a uh, simple wave. The most simple, the most basic wave. Okay, and if you see that it said here that modulating signal use the peak value of carrier as reference point. Modulating signal value adds or subtract from the peak value of the carrier. So for AM, remember when we do the AM modulations, that means the amplitude of the carrier, okay, the amplitude of the carrier change in accordance with the amplitude variation of the modulating signal. So what does it mean? So if the amplitude property of the carrier change, that means the high and low, okay, the high and low of the carrier signal will change according to the input signal variation. Okay, so there are another equation, what we call as the envelope. Okay, later you're going to see about this envelope. Okay, so the envelope is equal to VC plus VMT. Okay, so class, if you see from these equations, small small letter like this, small letter of VMT like this is a function. Whereas for capital letter like this is for a constant. Okay, so this is mathematics. In mathematics, normally if it is a constant, we use a capital letter. If it is a function, we use a small letter. Okay, so VC is a constant, the peak amplitude of the carrier, plus the input modulating signal, VM sine 2 pi FMT. Okay, so from the envelope signal, okay, the envelope signal is multiplied with the, sorry, the envelope signal is multiplied with the sine 2 pi FCT. And you're going to produce the final AM equations. Okay, so the final AM equation is this one. Okay, so you see that you have a modulator, okay, and you have the input signal VMT, okay, and you have the carrier signal VC of T, and you're going to produce VAM of T. Okay, so the AM signal is VC sine 2 pi FCT plus VM sine 2 pi FMT sine 2 pi FCT. And we need to change this part. We need to simplify this part. Okay, because this is sine and sine. So according to trigonometry identity, sine and sine, sine A, sine B function can be simplified into cos A minus B over 2 minus cos A plus B over 2. Okay, so therefore, we can rearrange the equations to be like this. Okay, so this is the first part that you have seen before, the carrier VC sine 2 pi FCT plus this part. So this is after we have done the trigonometry, we have simplified using the trigonometry identity. So sine and sine becomes cos minus cos. Okay, so this is Vm over 2 cos 2 pi Fc minus minus Fmt minus Vm over 2 cos 2 pi Fc plus Fm. Okay, so you see that this part, okay, Fc minus Fm, that means it is located at lower frequency, whereas this part is Fc plus Fm. So this is the upper frequency, the higher frequency. Okay, so the lower frequency we noted as lower sideband, and the high frequency we noted as upper sideband. And the first part is what we call as the carrier component. So you see that AM, this is double sideband full carrier, DSB FC. Double sideband full carrier signal has three components. Okay, the carrier, the lower sideband, and also the upper sideband. Okay, so how does the AM signal looks like? Okay, it looks like this. Okay, so this signal can be generated using the MATLAB. Okay, so you see the graph here is actually produced through using the MATLAB. Okay, if you have a MATLAB software, you can play around with the Simulink. There is a module, there is a AM module that you can use. Just drag the module and then you can see the output. How does the output looks like? Okay, so if you see from this graph, the first graph is the carrier. Okay, so this is VC, VCT, VC of time. Okay, function of time of carrier. And then we have the modulating signal or the input signal, VMT. And the last one would be the VAMT. Okay, so you see that class, for the VCT, it has a ripples. The ripples is very close one another, right? Compared to the VMT. So VMT, you see that the distance between the ripples is far away compared to the carrier, right? So because of this, you're going to see that the carrier, okay, this means that the carrier frequency is larger than the modulating signal frequency. Okay, if the ripples is very close one another, that means it is a high frequency signal compared to this VMT, where the ripples is far away from each other. Okay, and you're gonna see another thing for the VAMT. So for the VAMT, you see that there's a red color. Okay, there's a red color line over here. The red color line above and below, right? So this red color is actually the imaginary line. Okay, this is where we call it as the envelope. Okay, so you might wonder what is the envelope as mentioned here. Okay, the envelope has the upper side and also the lower side. So this is the red color line is actually the envelope. It is an imaginary line, so it is actually not exist. The line is actually not exist. Okay, so it is an imaginary line. So you see that the red line is called as an envelope. Okay, so the signal looks like it is inside the envelope. Okay, it is looks like as if it is inside the envelope. Okay, so we have the upper side envelope and also the lower side envelope. Okay, so the upper side here is a USB upper side band, and the lower side here is the lower side band. Okay, and the signals is look within the envelopes. Okay, and you see that what are the other things that you can find from here? If you ask me, we can also see the difference in terms of amplitude. Okay, since we are learning about AM, okay, we are learning about AM, so you see the difference about you see the difference in carrier. Okay, so if you see the carrier, initially it has a constant amplitudes. It has a constant amplitudes within the range of 10 volt, positive and minus 10 volt. Okay, but after modulation with the modulating signal, the amplitude of the carrier change in accordance with the input. Okay, so initially it's 10, so now it becomes within the range of 10 until here is 15, because 10 plus 5, so it's going to be the maximum going to be 15 volt in this example. Okay, and the amplitude below here is also within this one is minus 15. Okay, so you see that the carrier move from 0 to 10 until it reach the maximum 15. Okay, so the maximum value of the amplitude in this example becomes higher. Okay, 15 in this example. Initially is 10, now the maximum is 15. So that changes correspond to the information carried by the carrier. Okay, so if you ask me, this is a waveform. So we call this as waveform. Okay, so waveform is a signal in time domain. Okay, so waveform normally correspond to the time domain signal. What is time domain? Time domain is time versus voltage, like this. Okay, so this is a time domain signal. Okay, so in the exam, normally we ask the student to draw or to sketch the waveform, okay, or the frequency spectrum. Okay, if the question asks you to draw a waveform, that means you have to draw the um, the signal, the time domain signal, like this. Okay, time versus voltage. Okay, so this is waveform. But if the question asks you to draw a frequency spectrum, it gonna looks like this. Okay, so frequency spectrum is the wave, is the drawing of the wave in frequency domain. Okay, so it is actually F versus, you can say that this is the amplitude V. Okay, so how can we draw the frequency spectrum? So in order to draw the frequency spectrum, first you have to know the equations. Okay, you have to know the equation first. Then you can draw the frequency spectrum. Okay, so we already learned the equations. The equation is this one. Okay, so from the equations, you're going to see that we have three components. The first component is a carrier. The second component is the lower sideband, and the third component is the upper sideband. That means if you want to draw the frequency spectrum, we're gonna have three components, okay, like this. So the center is the carrier, okay, so this is the carrier, and the second component is the lower sideband. This is the lower sideband, and the third component is the upper sideband, okay. The frequency, the frequency of the component is the center would be the FC, and the lower sideband would be FC minus FM, and the upper sideband frequency is FC plus FM. What about the amplitude? The amplitude of the carrier is VC, and the amplitude of the lower sideband is VM over 2, while the amplitude of the upper sideband is VM over 2. How do I know this? Okay, it is stated in the equations. This one. Okay, so you see from here, from this equation, what you can get actually first is the frequency. Okay, so maybe I can use a different color, for example. So let's say I use a different color. So the first thing you can spot the frequency. You can spot the frequency carrier. You can spot the lower sideband frequency and also the upper sideband frequency. Okay, and then what? You can determine the amplitude of each component. The first one is the voltage of the carrier. The second one is the voltage of the lower sideband. The third one is the voltage of the upper sideband. So from the equations, then you can draw the frequency spectrum. Okay. So class, there are two things when you draw the wave in the exam, during the exam. When we ask you to draw, there are two things that we're gonna see. The first one is that whether you draw correctly. Draw correctly means that if the equation contains three components, that means you should have three components, not two component, not four component, five component, or etc. So if you draw three components for AM double sideband full carrier, that means your drawing is correct. The second thing I want to see is about labeling. Okay, when you draw, then you have to label. So what are the labels that I'm expecting? First thing is I'm expecting you to label the axis, which is the V versus F. Okay. Another thing I'm expecting you to label is the frequency and also the amplitude. Okay. In the exam, you might need to find the values instead of variable like this. Okay. For example, VM over 2 may be 5 volt, for example. And this one is maybe 20 volt, for example. So you have to put the values depending on the question. Okay. So normally in the exam, you will play around with the values, not the variables like this. So this is we learn in variables. But in the exam, you're going to see that you have to play around with the values. Okay. So after we draw, we can actually find a few set of parameters. What we can find from here actually. The first thing we can find is about the bandwidth. Okay. So the bandwidth of the double sideband full carrier AM is actually the higher frequency upper sideband minus the lower frequency. So USB frequency minus LSB frequency. Okay, so the upper sideband is FC plus FM minus the lower side frequency. So minus and minus are going to be plus over here. So that's why you get 2 FM. Okay, so what is 2 FM here? So you see that it is actually corresponding to the distance between the upper sideband and also the lower sideband. And you're going to see that the distance between carrier and the upper sideband is FM. And the distance between the carrier and also the lower sideband is another FM. So that's why you get the bandwidth, okay, the range, the distance from upper sideband to the lower sideband gonna be 2 FM, okay? So this is the bandwidth, okay? So uh, it said here that several baseband signal might be transmitted simultaneously on different carrier frequencies, multiplexing, providing the sidebands do not overlap, okay? So the information in the baseband information signal is duplicated in the LSB and USB. The carriers conveys no information. So what does it mean? So it means that, okay, class, that this means that, sorry. So the statement means that information only contained within the upper sideband and also in the lower sideband. Okay. In the upper sideband, we have information. Okay. And the lower sideband also contains the same information. Okay. So it is like a duplicated information. Whereas the carrier, okay, does not contain any information. Okay. The carrier itself, okay, the carrier itself does not contain any information. Okay, information only contains in the sideband. And you see that it is a duplicated information. That means information in the upper sideband is similar with is the same information as in the lower sideband. That means it looks like you are transmitting twice. Okay, in AM double sideband, it looks like you are transmitting the signal twice, as if you are transmitting twice, because the information is duplicated. So the receiver also received duplicated information. Okay, so double sideband, full carrier, we transmit the signal as if we transmit twice, as if. Okay, because the information in the upper sideband is similar with the information in the lower sideband. Okay, so another parameter is the modulation index. So modulation index is a parameter that want to determine the ratio of modulating signal amplitude and also carrier amplitude. So we want to measure the ratio of amplitudes. Okay, the ratio of amplitudes. So it is said here that in most of the time, okay, the the modulation index, okay, contains a VM and also VC. So this VM and also the VC is actually the peak amplitude of the signal. Okay, so again, if I draw the signal, okay, the sine wave, okay, this is a sine wave. So the peak amplitude, for example, here is Vm. Another one is minus Vm. So this is the VMT. Okay. So this is time versus the voltage. And another one, if I draw the carrier, for example, okay. So carrier, so this is VC, the peak amplitude in the positive side, while in the negative side, we also have the negative VC. Okay, so this is for the VC of T. Okay, so this is a V versus T graph. Okay, so in most of the time, the peak amplitude of the modulating signal is less or equal to the peak amplitude of the carrier. Okay, so it's said that as proper double sideband full carrier. So modulation index, when we want to measure the ratio of amplitudes, okay, input and carrier. So M is equal to peak amplitude of the modulating signal divided with the peak amplitude of the carrier. Okay, so this is actually volt divide with volt, which means that it produces a unitless, okay, it produces a unitless value. Okay, this is a ratio. Okay, volt divide with another volt, so you're going to produce a unitless value, a unitless parameter, which is the M. Okay, so M modulation index also can be represented as in terms of percentage by multiplying with 100%. Okay, so this M, you see that you use a capital M here, okay, for the percentage. Okay, so be careful about this, class, because based on the previous semester's experience, students are confused on how to calculate this simple parameter. Okay, so I will show you what are the careless mistakes of the previous semester students. Okay, so I will show you using a different color, for example. So in the previous semester, students make careless mistakes like this. The first careless mistake is that students wrote the equation like this. VC over VM, okay, is inverse. So it is wrong. Okay, so this is wrong. Another thing is that students wrote like this. M equal to VM sine 2 pi FMT divide with VC sine 2 pi FCT, which is also wrong. Okay, so you just need to put the peak amplitude only in the equations. So this is wrong and this is wrong. Okay, so make sure you write properly. M equal to peak amplitude of modulating signal divide with peak amplitude of the carrier. Okay, then you're going to see that modulation index also give us um, information about the AM scenario. Okay, so there are three types of uh, AM modulation. I mean, don't be confused, because we have AM double sideband full carrier, AM double sideband suppressed carrier. We also have single sideband. We also have vestigial sideband, as stated in the previous slide. But now, if we see from the perspective of modulation index, we can determine three types of scenarios, okay, based on the modulation index. So the first one is when the value of modulation index is less than 1. Okay, if the value of modulation index is less than 1, that means we call it as under modulated AM. Okay, so that means in this case is VM is actually less than VC. So that's why you get less than 1. And another case is M equal to 1, the ideal case. Okay, so for ideal case, this is means that VM, the peak amplitude of modulating signal, is equal to the peak amplitude of the carrier. Okay, so it is the ideal case. Another one is M larger than 1. Okay, the third scenario is M larger than 1. We call it as overmodulation. So this is when Vm is larger than the Vc. Okay, so that's why you get the overmodulation. So how does the scenario looks like? It looks like this. Okay, so we have asked these questions before in the previous semesters. In the previous semester, we asked the students to explain, okay, about the types of modulations, okay, the types of the scenarios of AM modulations, and also sketch the drawing. Okay, so the answer of that question would be in this slide. Okay, because previously we have asked this in the questions. So you need to explain maybe either one of these. What is the undermodulated AM, or what is the ideal AM or overmodulation? Okay, and we also have asked the students previously to differentiate the three types of AMs. Okay, so you have to explain all of this. Okay, in order to differentiate between the AM, under modulation, ideal modulation, and also the over modulation. Okay, so for under modulation, M less than 1, that means the peak amplitude of the message is less than the peak amplitude of the carrier. Okay, signal strength obtained at the receiver is not exactly the same as the signal strength at the transmitter. That means the signal strength at the receiver is less than the signal strength at the transmitter because of the attenuations. And there is no distortion to the signal, just reduce in signal strength. And the graph looks like this. Okay, so you're going to see that most of the time it is actually under the category of under modulation. So this is a normal scenario. Okay, normal scenario. Okay, and you can draw the graph like this. Okay, so this is the graph that we have seen previously, okay, in the previous slide, which is the under modulation. Then for ideal modulations, for ideal case, where you can uh, transmit with more stronger signal strength, okay, Vm equal to Vc, okay, it will produce the greatest output power at the receiver without distortion. Maximum info signal amplitude is transmitted. So more info signal power is transmitted, produce stronger and more intelligible signal. Okay, so actually this is a good scenario. Okay, a higher value of Vm is good actually. Why? Because the modulating signal contains the informations, whereas the carrier does not contain any informations. So it is good actually to have a high value of Vm. Okay, so and you're gonna see that this achieve a 100% of modulation index. So the graph looks like this. So the difference would be at this part. Okay, you see that this part is close, very close, upper and lower side. Okay, maybe I use a different color. Wait. So the difference you're gonna see is over here, this part, this one, compared to the under modulation. You see that this one is smaller. Okay. Then we have another, the third type is over modulation. Okay. So over modulation, Vm is larger than Vc. Okay. As I said previously that larger Vm is good, but if the Vm is bigger than the VC, so this will cause the distortion. So it is actually not good if the VM is more than the VC. A high value of VM is good, but not too high. Okay. And then you're going to see that this will cause a distortion. So negative peak has been clipped off. The original shape of the signal will be destroyed. Okay. So you see that this is the clip off signal. Okay. The clip off signal part. Okay. So we try not to use this. We try not to achieve this over modulations. It is good to do the under modulation or the ideal modulation. Okay. So modulation index can also be calculated by measuring the height of the signal. Okay, the height of the transmitted signal. And you see that if you see from this graph, so this is a AM signal. This is the AM signal. So in AM signal, you see that it has um, a positive part and also the negative part. Okay, so positive part, the upper side, and the lower side is the negative part. Okay, and we have a few set of parameters, what we call as a Vmax. So Vmax is calculated from the x-axis until the highest amplitude. Okay, until the highest amplitude. So we call it as a Vmax. Another parameter is Vmin. Okay, so Vmin is measured from the lowest amplitudes. Okay, the lowest amplitude would be this part. Okay, so it is measured from the lowest amplitude until the x-axis. Okay, so this is the Vmin. Okay, and if you see another thing is the VC. Okay, so VC, carrier peak amplitude, is measured from the x-axis until the center of the ripples over here. So you see that this is the upper part. If I use a different color, okay. So the upper part is actually looks like a sine wave. If you see from this envelope shape, okay. So it is like it looks like a sine wave. Okay, center at this part. This is the center. So VC is actually the center of this envelope until the x-axis. So this is VC. Okay. And what about the VM? Okay. So the VM is actually the distance from the peak until the center of the envelope. Okay. So this is VM. Okay. This is also VM at the lower side. VM. Okay. So Vmax, okay. So Vmax is actually equal to VC plus VM. Okay. Vmin is actually equal to VC minus VM. Okay. And if you want to use VM and VC, you can also write like this. VM is equal to Vmax minus Vmin over 2. VC is equal to Vmax plus Vmin divided over 2. Okay. So therefore, the uh, the modulation index M is actually equal to Vmin of divide with Vmax. Okay, sorry, Vmin. Okay, okay, sorry. Modulation index is equal to Vmax minus Vmin. Okay, which is this is actually corresponding to Vm divide with Vmax plus Vmin. This is corresponding to the Vc. Okay, so I can say that this is the second equations of modulation index. Okay, the first equation is M equal to Vm over Vc. M equal to Vm over Vc. The second equation is this one using the Vmax and Vmin. Okay, and if you see from this graph, the second graph like this, um, it shows you how to calculate using the peak-to-peak values. Okay, the peak-to-peak values. Peak-to-peak values means that we also consider the negative side as well. So from positive side, the maximum positive until the minimum negative. So that one is a peak-to-peak. Okay, so if you're using peak-to-peak, that means you have to change this one into peak-to-peak values. That means M equal to Vmax peak-to-peak minus Vmin peak-to-peak divide with Vmax peak-to-peak plus Vmin peak-to-peak. Okay, so this is the modulation index. So for your information, in the previous semester, we have asked these kind of questions, okay, where we give the student a graph of signal. Okay, we give the students a graph of signal, and from that graph, the students need to determine the modulation index. Okay, that means the students need to find the maximum value or the minimum value or the VC or the VM in order to calculate the modulation index and another parameters. Okay, so this has been asked previously. Okay, we have asked this kind of question before. That means you have to know, based on the graph, you have to be able to extract the Vmax, the Vmin, the Vc, and also the Vm, so that you can calculate the rest of parameters. Okay, so I also want to show you how can we draw the waveform. Okay, how can you draw this waveform actually? In the exam, how should you draw in the exam? Okay, it looks complicated if you draw using a hand, by hand, because this is a graph drawn by the software MATLAB. Okay, but in the exam you have to draw using by hand. So how to simplify this process? Okay, so normally I would ask the student to draw like this. So for me, what I will do is that maybe is there any wait. I'm trying to find an empty spaces. Okay, so that I can draw. There's no much empty spaces, so maybe I can draw here. Okay, I will draw here. So when you want to draw the waveform of AM, what you can do is that first you can draw the axis. Okay, so you can draw the axis like this. Okay, so this is the axis V versus T, for example. Okay, then what you can do, for me, I would like to draw another axis. Okay, the envelope axis. Okay, so I will make it like this. Something like this. I'll make a dotted line. the center of the envelope. Okay. So the center of the envelope is actually the VC. Okay, the center of the envelope is actually the VC actually. Okay. Then what I will do is that I will make another dotted line of sine wave like this. So this is an imaginary line to guide me to draw the signal. Okay, and I also will draw the another dotted line over on the negative side. So I will do like this. Okay. So after I do like this, then I can draw the signal. So let's say I use a black color. So when I draw the signal, I can draw like this. So you see that I don't use any ruler. Okay. Don't use any ruler in the exam. It's going to waste a lot of time. Okay. So if you practice, you can do the sketch of this signal. Okay. There it is. So this is a double sideband full carrier. And when you draw like this, I want you to label. First, you have to label the axis. Then you can label another things. What color should I use? For example, this one. So when you label, you can label the maximum value over here, which is the Vmax. Okay. So Vmax is the VC plus VM. Okay. Another one, you can also label the Vmin. Okay, Vmin. So here is the Vmax minus Vmax, and over here is the minus Vmin. Okay, so if you draw like this, that means you can get uh, the full marks for these questions. Okay, sorry if I complete this graph, it looks like this. Okay, something like this. Okay, so this is AM waveform. Okay, AM waveform. And another one is AM spectrum. Okay, so I will draw another graph which I call the AM spectrum. Okay, remember when you want to draw the AM spectrum, you have to determine the equation first. Okay, so since we already given the equations, this one, AM equations, then we can draw. Okay, so when I want to draw the AM spectrum, there are two things I need to find from the equations. The first thing the first thing I can get from the equation is the frequency. Okay, the carrier frequency, the lower side frequency, and the upper side frequency. The second thing that I can find is actually the amplitude of the signal. Okay, so you see that I can find the amplitude of the carrier, then the amplitude of the lower side frequency, and the amplitude of the upper side frequency. Then I can draw. Okay, so when I draw like this, okay, so this is V versus F for frequency spectrum. So since I have three components, so the first one is the carrier. Sorry. Okay, the first one is the carrier located at FC with the amplitude of VC as stated in the equation. Then I can also draw the lower side, band, which located at FC minus FM, and the amplitude is MVC over 2. So in this case, this is MVC over 2. Okay. Another one, from the equations, I can draw the upper sideband. The upper sideband is located at FC plus FM, and it has the amplitude of MVC over 2. Okay, so this is what we call as the amplitude spectrum. Okay, if you remember that previously, in the previous equations, if you see from the previous equations, we use the Vm over 2, right? Vm over 2. But if we replace Vm over 2 with MVC over 2, okay? So you see that, how can we get a MVC over 2? MVC over 2 is from this part, from the modulation index equations. Modulation index is Vm over Vc. Okay, so that means Vm is equal to MVC. Okay, so that means this is also equal to the, so if I make a slash, this is also Vm over 2. Okay, so you can also write a Vm over 2. Okay, in the exam, we might also ask you to find a power spectrum. Okay, there's an amplitude spectrum and there's also power spectrum. Okay, so for power spectrum, that means your graph should be in terms of power. Okay, so it can also be P versus F. Okay, where you need to write the power, the carrier power, EC, how much is it, the PLSB, and also the PUSB. Okay, so that one is for the power, where you will learn later after this. Okay, so now is the amplitude spectrum. The graph below here is what we call as the waveform. Okay, whenever you heard the name of waveform, it is actually a graph of time domain, V versus time. Whenever you heard about spectrum, frequency spectrum, that means it is a graph of frequency domain. Okay. Okay, let's do the example. Okay. Before that, can I get your response? Students, are you still there? Can you hear my voice? Can you see my screen?
Yes, doctor.
Okay. Sometimes I feel that I'm talking to myself, okay, because you're very quiet, okay, you're very quiet. I'm not sure what you are doing right now. Hopefully you are still listening, okay, because I'm explaining the most important thing, okay, for your project and also for your for your project and also for the exam, okay. So let's do this example, okay. So of course you need a calculator. You need a calculator to try. So you have to check my answer. Okay. Your job is to check my answer. If my answer is wrong, maybe because of typo or I forgot to write something, then you have to inform me. Okay. So example 3.1. Okay, class. For the online class, I'm not taking a break. Okay. For you, you can take a break on your own. Okay, because I believe if you want to eat something, you can go to the kitchen and get a drink and get a food, so that you can also uh, eat and drink during the class session in front of your laptop. Okay, there's no problem. You don't need to go far away. So feel free to have your own break, your own break. Okay, you can have a break on your own. But for me, I will keep on continue until maybe 1:45, another 1 hour. Okay, and then we can dismiss. Okay, and this lecture will be recorded, and I will share the recorded session later to you. Okay, so example 2.1, if you see from here, a carrier signal with a peak voltage uh, of 2 volt. Okay, so you see that you are given a peak, sorry, a peak, a carrier signal with a peak voltage. What does it mean? So that means you are given a carrier which has a voltage peak voltage VC of 2 volt. Okay, it is amplitude modulated with another signal. So that means this carrier is modulated with another signal. So that another signal is what we call as the modulating signal. Okay, so if this is a modulating signal, that means this is the modulating signal frequency. Okay, 10 kilohertz. Then the modulation voltage has an effective value of 750 millivolt. Okay, modulation voltage. Modulation voltage here means that this is referring to the VM, but this is VM effective, not the VM peak. Okay, so how to calculate the VM peak? Okay, so VM effective is actually this one is VM effective is actually equal to VM peak divide with square root of 2. Okay, so if you want to find the peak values, that means you have to multiply the effective value with the square root of 2. Okay, so in our calculations, we normally use to find the VM peak. So if I want to find the VM peak amplitude, that means this is 750 millivolt multiplied with square root of 2. So how much would be this one? So 750 milli multiplied with square root of 2. So I'm gonna get 1.06. Okay, volt. So this is the peak amplitude of modulating signal. So the question asks you to find the percent modulation. That means I need to find M, the value of M equal to Vm peak amplitude divided with Vc multiplied with 100%. Okay, so this is equal to 1.06 divided with 2 volt multiplied with 100%. Okay, so 1.06 divided with 2 times 100. So you're gonna get this is around 53%. Right. Yeah, 53%. And then the question asks you to find the instantaneous voltage of the positive and negative envelope. When the 10 kilohertz has completed 68 microsecond of the cycle. What is this actually? Okay, the positive and negative side of the envelope. Okay, so at 68 microsecond, actually the line will cut through the positive and negative envelope. How does it looks like? So we have to go back. So we have to go back to to this part. Okay. So the envelope, as I mentioned, that we have the upper envelope, the upper side envelope, and the negative side envelope. Okay. And if you see, for example, at time 0.03, for example, if we make a straight line, okay, if we make a straight line like this, the line will cut at the positive side of the envelope and also at the negative side of the envelope. Okay, so this is the thing that we need to find. How much is the value of the positive and negative side at 68 microsecond? Okay, so in order to find the envelope, we have to use the envelope equations, equation 2.3, okay, which is VC plus VM sine PMT. And for your information, okay, for your information, this envelope can be positive, okay, it can be positive or negative, okay. That means I can write like this, V envelope equal to positive, negative VC plus VM sine 2 pi FMT. Okay. So if we go back to the slide, okay, the slide, go back. So you see that the envelope, okay, the envelope is equal to VC plus VM sine 2 pi FMT. And there is a positive and negative over here. Okay. So we can write VC. So if you see that if I draw V envelope, this is plus minus VC plus VM is 1.06. Okay. Sine 2 pi FM is 10 kilo. Okay, FM is 10 kilo. So if this is times 10 kilo, 10 times 10 power of 3 multiplied with T, the time. T is 68 times 10 power of minus 6. Close bracket, close the big bracket. Okay. So you see that the time, okay, the time here, this is the 68 microsecond that you have to put in. Okay. So how can we calculate this? So in order to calculate this, that means you have to change your setting in the calculator setting to be in terms of radians. Okay. For me, I choose I have to press mode 3 times. Sorry, 4 times mode for me. So I choose radians. Okay. So I have to solve the sine part, this sine part. Okay, sine 2 pi times frequency 10 kilo times the time 68 microsecond. Okay, so let's try together. Okay, so first I have to write 2 pi. Okay, for me I write I have to solve the bracket first. the sine function first, so that easy for me to calculate. Okay, so 2 pi, so I write 2 pi times 10 kilohertz, 10k, times 68 microsecond. Okay, and then I write sine of answer. Okay, sine of answer, I gonna get negative 0.9048. So that means I will rewrite like this. So it is equal to plus minus in bracket, okay, 2 plus 1.06 in bracket minus 0.9048. Okay, so this is I multiply with 1.06. Okay, 0.9048 I multiplied with 1.06. Okay, so I get negative 0.9591. Okay, so this is actually 2 minus, okay, 0.9591. Okay, please correct me if I'm wrong. So this is equal to plus minus, okay, so 2 minus, okay, 2 minus 0.9591, 2 minus 0.9591. So I'm gonna get 1.4, 1.0409. Okay, volt. Okay, so that means, okay, that means if I go back to the previous slide, if I go back to the previous slide, okay, just want to show you. For example, class, for example, this is 68 micro, for example, okay, and we draw a straight line like this. So the graph would cross at positive 1.0409, and the other one, the graph would cross at negative 1.0409. So it looks like this, okay, if this is the real graph. So I just want to use this graph. So let's say that this is a 68 micro, and you draw a straight line, and it will cut at 1.0409 volt, positive and negative side. Okay, then we go to the slide again. Okay, we go back. The question asks you, the third question, the third question asks you to draw, to illustrate the resulting AM waveform. So the terms here is AM waveform. That means you have to draw a time domain signal. Okay, so as I have teach you before, okay, so you draw a, you make a simple drawing. Okay, so this is something like this. So my signal looks like this. Okay, and as I said that you have to label V versus time. Okay, V versus time, and you have to label the peak amplitude V max and also the V min. Okay, this is minus V max, and this is minus V min. Then complete. So actually you can determine the Vmax and Vmin actually. Okay. Actually you can determine the Vmax and Vmin. But how to do that? Okay. So if you see from this question that Vmax is actually equal to Vc plus Vm. So this is actually 2 plus 1.06. Okay. So I get 3.06 volt. While the V min is actually Vc minus Vm. So this is 2 minus 1.06. So 2 minus 1.06. So you get 0.94 volt. Okay. So you just need to label this Vmax and Vmin, then complete. Okay, complete. So we're gonna learn the next the next topic is about power calculation. So class, do you have question about this? Can I get your response about this? Is it okay? Can you understand?
Okay, doctor.
Okay. So if you don't understand, you want to further discussions, further explanation, please ask me. Okay. So if there's no questions, that means you understand this, which is very good. Then we can move to the next topic, which is the power calculation. So this is very important. Okay, the power calculation. So power is equal to V square over R, or V square over 2R. So if you use the RMS voltage, that means we divide with R. If we use a peak value, peak voltage, we divide with 2R. Okay, so power calculation is still the same from long time ago until forever, based on the Ohm's law. V equal to IR. That means the power is either V square over 2R, or you can also write V times I, or you can also write I square R. Okay, so for this purpose, we are using the voltage, the amplitude. Why? Because we are learning about the amplitudes. That means we are playing around with the voltage. Okay. So you see that uh, in order to calculate the voltage, okay, in order to calculate the voltage, the first thing you need to know is the equations. Okay. I always advise the student, when you want to calculate the power, make sure you already define the equation. Okay, so what are the equations? The equations is from the previous slide. So if I go back to the previous slide, okay, if I go back to the previous slide, this is the equations. Okay, this is the equation. So once I know the equations, then I can calculate the power. Without equations, you don't know how to calculate the power, because the information is here. Okay, you can find the voltage, you can find the frequency over here. Okay, so for double sideband full carrier, if you see from here, class, the total power, since we have three components, right? So that means the total power is equal to the power of each component, the summation of power from each component. That means we have the PC, power of the carrier, plus power of the lower sideband, plus power of the upper sideband. Okay, so how to calculate power? So that means for PC, you see that the amplitude is VC. The peak amplitude is VC. That means it is VC square divide with 2R. Okay, plus plus Vm over 2 square divide with 2R plus Vm over 2 square divide with 2R. So you get the total power. Okay. And if we go back to the slide, go back again. Okay. So you see that this is for the double sideband full carrier, where we have the three component, right? So again, if you draw the the signal, the frequency spectrum, if you draw, this is a V versus F. Okay. So you're gonna have this VC, and this is the uh, lower sideband and also the upper sideband. So this is FC minus FM. This is FC plus FM. Okay. So as I say that this is VM over 2. Okay. Or you can also write in terms of MVC over 2. Okay, if I use a different color, that means that this is also MVC over 2. Okay, this is also MVC over 2. Okay, so that's why when you want to write the equations, that means this is VC square over 2R plus MVC over 2 square divide with 2R. Okay, so that means this is a VC square over 2R plus MVC over 2, okay, MVC over 2 square divide with 2R plus MVC over 2 square divide with 2R. Okay, so MVC square over 2R, MVC over 2 square. So this is actually M square VC square over 4. So you're going to see that it is actually this part. Okay. The upper part is actually this one. This is the upper part. MVC over 2 square is actually this one. Okay. And then you divide with 2R. Okay, so you see that if we see the equations has the carrier power component. Okay, each of it has a carrier power component. What is the carrier power component? The carrier power component is this one. Wait, so I use a red color. So this is the carrier power. Okay, we also have this carrier power component, VC square over 2R. Okay, so that's why we can rewrite the equation as PC, the carrier power, plus M square over 4 PC plus M square over 4 PC. And if you rearrange, you can find these equations. Okay, P total equal to PC in bracket 1 plus M square over 2. Okay, and remember class, this is only true for double sideband full carrier only. Okay, this is for double sideband full carrier only. The rest of AM, when you want to calculate the total power, again, as I said that you have to you have to do the summation of all the power component. Okay, we have the PC, we have the lower sideband, and we have the upper sideband. Okay, this one. Ideally, in general, it is like this, but for double sideband full carrier, you can make it as like this. P total equal to PC plus M square over 2. Because later, okay, you're going to see that another type of AM, the component is not three component, maybe two component, maybe one component. Again, it is based on the equations. So when you want to write the power equations, you have to know the BAM equation first. Once you know the equations of the AM, then you can determine the power and other parameters. Okay, so why do I write three components? Because the equation contains three components. So that's why when we write the power, it is PC plus PLSB plus PUSB. Okay, and this one. So you see that from these pictures, so I think we already learned the upper side. So if I draw a line like this, so power of the lower sideband is equal to the power of the upper sideband. Okay, which is equal to Vm over 2 square divide with 2R. Or you can also write MVC over 2 square divide with 2R, which will cause you to have this one. Okay, M square VC square over 8R. Okay, so this is actually the same from here actually. So this is M square, is what it? So this is actually M square VC square divide with 8R. Okay, and then what? If you see the equation below, so the equation below is to answer the statement given in the AM disadvantage. Okay, so here you're going to see why the AM is considered as wasted of power. Why? Okay, because of this. Okay, so now we want to see that how does the double sideband full carrier wasted of power? How can it be? Okay, so we have to see from the ideal perspective. Okay, ideal scenario. Okay, the ideal scenario is M equal to 1, where the VM is actually equal to VC. Okay, so if the VM is equal to VC, and from the equations, you can see that uh, this one, if M equal to 1, from these equations, from PT equal to PC plus M square over 2. So PT is equal to PC in bracket 1 plus M square over 2. If you put M equal to 1, okay, if M equal to 1, that means your PT, P total would be 3 over 2 of PC, where the PC itself is actually 2 over 3 of the total power, okay, as stated here. So you see that the carrier itself contributes to 2 over 3 of the total power. That means we have the remaining 1 over 3 of the total power for the sidebands, both the upper and lower sideband. So that means this is P LSB plus P USB is equal to 1 over 3 of the total power. Okay. So therefore, since PLSB is equal to PUSB, so we just need to divide with 2. Okay. 1 over 3 divide with 2. So we're going to get 1 over 6. Okay. 1 over 3 you divide with 2. You're going to get 1 over 6. So each sideband only has 1 over 6 of the total power. Okay. Which is very small. Okay. 1 over 6 is only for the lower sideband, and 1 over 6 of the total power is for the upper sideband. Very small. Okay. So this is for the ideal case. But if it is not in a non-ideal case, it's going to be worse. Okay. For a non-ideal case, that means the power of the sideband would be even less than 1 over 6 of the total power. Okay. Why? Because if M less than 1, that means Vm is less than Vc. Okay, for that reason, we're going to have a much lower power for the sideband. Okay, and for your information, the higher the power of the sideband actually would be better. Okay, if the power of the sideband is higher, it would be better for our transmission. Why? Okay, because the sideband contains information. Okay, the information is contained within the sideband. So if you have a high power of sideband, it would be good. Okay, but now the situation for double sideband full carrier, the carrier power is very small, while the carrier power is very big. Okay, and as I said previously, that the carrier does not contain any information. Okay, the carrier itself does not contain any information. The information only contains within the sideband. Okay, and you're going to see that. So if the carrier does not contain any information, why does it consume a lot of power? Okay, so that means the carrier consume a lot of power, but it does not carry any information. That means we're going to waste a lot of power only on the carrier side. Okay, so this evidence prove that the previous statement, as stated in the previous statement of AM disadvantage, that the double sideband full carrier wasted a lot of power on the carrier component, where the carrier component does not contain any information. Okay, so this answer the previous statement. So if I go back to the previous statement, okay, the disadvantage, okay, this one. So the disadvantage is said that it is wasted of power in the carrier side, where the carrier does not contain any information. So, so that means this is for double sideband full carrier, we are wasting a lot of power in the carrier power in the carrier side. So that means we are transmitting more than enough power. Okay, because the information only contained in the sidebands, but we are transmitting more than enough power from the transmitter to the receiver if we use the double sideband full carrier. Okay, so if it is not a ideal case, that means the power of the sideband going to be much lower, and we're going to consume a lot of power only in the carrier component. So which is disadvantage for the double sideband full carrier in some applications. Okay. So I go back to the slide. Okay. Okay. So let's do the example 3.2. Okay. Example 3.2. A 400 watt of carrier is modulated to a depth of 75%. Calculate the total power in the modulated wave. What does it mean? So you are given a carrier power PC. You are given a parameter of depth. Depth means modulation index. Okay. 75% or 0.75. Okay. So M is actually equal to 0.75 or 75%. Okay. So calculate the total power. That means we need to find the total power. How much is this? So this is an example of AM double sideband full carrier, because we are still learning AM double sideband full carrier. Okay, so we can use these equations. P total is equal to PC plus M square over 2. Again, remember that this is only true for double sideband full carrier only. If this is for double sideband full carrier, then we can use these equations. Okay, so put inside the value, PC equal to 400, M is equal to 0.75. Be careful, class. Don't put 75 square, which is wrong. Okay, 75 is for the percent. Okay, but for the calculation, you have to use the absolute number. Okay, 0.75. So you get the 512.5 watt. Okay, so this is a straightforward question. Okay, straightforward question. So let's do the next example. Example 3.3. Okay, so let's do together. Okay, class. Wait, Okay, example 3.3. So this is also about AM double sideband full carrier. Okay, so an AM broadcast. Okay, so the term AM here is referring to the double sideband full carrier. Okay, peak carrier voltage. Okay, peak voltage of 2000 volt. Okay, that means the VC is equal to 2000 volt. Okay, and then what? This carrier, okay, this carrier has been amplitude. So this carrier has been amplitude modulated to an index of 75%. So this is M, okay, with a 2 kilohertz of test tone. Okay, so carrier is modulated with another signal of test tone. So the test tone is actually referring to the modulating signal. So imagine you have a carrier, you modulate it with another signal, which is a test tone, which has a frequency of 2 kilohertz. So this is referring to the modulating signal. So therefore, this is actually referring to the modulating signal frequency, 2 kilohertz. Okay, so FM is 2 kilohertz. And then the station is broadcasting with a frequency of 810 kilohertz. What does it mean? The broadcast frequency from the radio station is actually referring to the F carrier, the carrier frequency. Okay, remember, the frequency that you use for transmission is actually referring to the carrier frequency, because our carrier is actually a radio frequency range. For AM, the carrier frequency should be within the standard range. Okay, 576, I think, until 1605, is it? Kilohertz. So that one is actually referring to the range of carrier frequency. Okay, the range of carrier frequency. So we have been given a lot of parameter values. Then we can calculate the other parameters. Okay, compute the lower and upper sideband frequencies. So therefore, the answer is here. Okay, so F LSB is equal to FC minus FM. Okay, so this is 810 kilohertz minus 2 kilohertz. Okay, so this is 808 kilohertz. Okay, F USB is equal to FC plus FM. Okay, then this is 810 kilohertz plus 2 kilohertz. So you get 812 kilohertz. Okay, it's easy, right? So this is simple. Okay, the next question is the peak voltage. Okay, peak modulation voltage, VM. So how can we find that? Okay, so M, so we can find this based on the value of M. M is equal to VM over VC. So therefore, VM is equal to M VC. Okay, so this is 0.75 multiplied with 2000. Okay, so you will get the value equal to how much? 0.75 times 2K. So 1500 volt. Okay. Class, can I get your response? Can you follow my explanation?
Yes, Doctor.
Okay.
Yes, Doctor.
Yes, sir.
Ha? Ada soalan ke? You have question? No. Okay. Ada soalan ke tadi? Tadi macam ada someone yang bertanya soalan. Kalau ada yang bertanya soalan, can you please repeat the question? I cannot hear the previous one. So if it is not a question, then I will proceed. So the next question asks you to find the peak, lower and upper. So VM, as we know that for double sideband full carrier, sorry, VLSB, VLSB, as we have learned previously, is equal to VM over 2. Or you can write also MVC over 2. Okay, you can also write MVC over 2. Okay, so VLSB is equal to VUSB is equal to VM 2. So that means this is 1500 divided with 2. So you get 750 volt. Okay. So easy, right? So this is easy. And then what? The maximum signal amplitude, Vmax. So Vmax is equal to Vc plus Vm. So this is actually 2k volt plus 1.5 kilovolt. Okay, so you get 3.5 kilovolt. Okay, what about Vmin? So Vmin is equal to Vc minus Vm. Okay, so this is equal to 2002 kilovolt minus 1.5 kilovolt. Okay, so this is uh, 0.5 kilovolt. Okay, is it okay? Can you understand this? Can I get your response?
Yes, Doctor.
Okay. Anybody wants to ask question? So if no questions, that means you understand. So this is an easy example, and we can try another example. So the explanation is here. The explanation is given here. Okay, so I already explained the answers. Okay. Example 3.4. So this is also a good example for exam. Okay, this is also a good example uh, for the exam. Okay, so let's try to do this together. Although the answer is already here. Okay, so example 3.4, a spectrum analyzer with input impedance of 50 ohm. Okay, so this is R, is used to measure the power spectrum of AM signal. So whenever you see AM signal, so this is actually referring to the double sideband full carrier. Okay, at the output of the pre-amplifier circuit, the AM signal has been modulated with a sine wave. Okay, so that means we are using a sine wave for the modulation. Okay, the simplest form of signal. Okay, the simplest form of signal is a sine wave. The effective power PC is 745 milliwatt, and each sideband PUSB and PLSB is equal to 125 milliwatt. So you are given the R values, resistance, you are given the PC, carrier power, lower sideband and upper sideband power. So that means it's easy, okay? So the first question, calculate the total effective power. Remember that P total is actually equal to PC plus PLSB plus PUSB. Okay, because we already learned from the previous slide. Okay, so class, if this is a double sideband full carrier, that means we have three components, right? The carrier, the lower sideband, and the upper sideband. So how do we know that we have three components? You have to determine the equation first. Okay, for this question, I don't need to prove the equation first, because the question already gave me the hint. Okay, the fact that this is a double sideband full carrier. So if double sideband full carrier, of course we have three components: the carrier, lower sideband, and also the upper sideband. Okay, so that means this is equal to 745 milliwatt plus 125 milliwatt plus 125 milliwatt. Okay, so 745 plus 125 plus 125. So you get 995 milliwatt. Okay, please check the answer. Make sure if it is wrong, please correct me. Okay, so uh, the next question. The next question asks you to find the peak carrier voltage. Okay, the peak value. Okay, so as we have learned previously that PC is actually equal to VC square divided with 2R. That means the peak amplitude of the carrier square divide with 2R. Okay, so that means VC, okay, VC is equal to PC times 2R and then square root. Okay, so PC times 2R and then square root. So therefore, this is 745 milliwatt multiplied with 50 ohm. Okay, so how much is this? So 745. So sorry, this is supposed to be square root. Okay, times 50. So 745 milli times 50, and then square root of answer. So you're gonna get 6.103 volt.
Doktor,
Yeah.
uh,
Oh,
10
sorry,
minutes
2R
to us.
okay. Si baik you betulkan. Kalau tak dah salah sampai habis semester. Okay. Okay, so this is 745 times 50 times, times 2. So saya buat macam ni lah 2 times 50 ohm. Okay. So 745 milli times 100. Okay. And then square root of answer. So you're going to get 8.6313 volt. Okay. Can you get the same answer?
Yes, Doktor.
Okay. And then what? Then the question asks you to find the modulation index, M, and the percentage modulation. Okay. So M is equal to MVC. Okay. So we don't know how much is VM. Okay. VM is the next questions. So actually we can write so M is equal to VM over VC, right? So this is actually equal to okay. So that means we have to find the, can we write from PC? So we need to determine this one first. Okay. So we don't know about VM, but we can find VM actually. Okay. We can find the VM. We know the VC, so that means this is you can use the, you can also use the equations. You can use this these equations if you want. P total is equal to PC 1 plus M square over 2, right? So M, that means we need to find the value of M. So M is equal to PT over PC. So that means we need to rearrange the equation. You can use like this. So M is equal to PT over PC minus 1, okay, times 2, and then square root of answer. Okay, square root of answer. Is it? So this is also used like this. Okay, PT over PC minus 1 times 2 and then square root. So therefore, total power is equal to 995 divide with 745 milli minus 1 and then multiplied with 2. So remember that this is also milliwatt. This is milliwatt. So milli and milli, so you can cancel the milliwatt. And then minus 1 times 2 and then square root. So you're going to get 0.8192. And if you want to make it in terms of percentage, that means you have to multiply it with 100%. Okay, so that's why we get 81.92%. Okay, 81.92%. Okay. So this is actually 0.8192, right? 8192. And this is equal to 81.92%. Okay. What about VM? So VM is actually equal to MVC over 2. Okay. So what you can do is 0.8192 times VC. How much is VC? We already get VC previously, 8.6313, and then divide with 2. How much is this? So 0.8192 times 8.6313. So you're going to get equal to 7.0707 volt. Okay, 7.07 volt. Can you get the answer?
Yes, Doctor.
Okay. Easy, right? And then what? The lower and upper sideband voltage, VLSB and VUSB. So VLSB, and we can determine based on the power value, based on the power. Or you can write MVC over 2. Okay, so if you see from here, the lower and upper sideband voltage. So as we have learned previously that VLSB is equal to VUSB equal to VM over 2. Okay, equal to VM over 2. So, so VLSB, so if I write here, so if I just write over here, so VLSB is equal to VUSB. Okay, so this is equal to VM over 2. Okay, peak amplitude divide with 2. So this is actually equal to 7.07 volt divide with 2. Why divide with 2? This is as stated in the previous equations that we have learned in the previous slide. Okay, So therefore, if you write 0.0707 divide with 2, so you're gonna get 3.535 volt. Okay, 3.535 3.535 volt. Okay, am I correct? Let's see the answer. Yeah, this one. Okay, so the LSB and USB we calculate using the peak value, not the RMS value. Okay, we calculate using the peak value, not the RMS. Okay, and then what? Sketch the waveform that you can see with an oscilloscope if it were placed in parallel with a spectrum analyzer. So the question asks you to draw the waveform. So how to draw the waveform? Okay, as I said that you can, as I teach you before, that you can do like this. Okay, draw the axis and then draw the imaginary line, upper and lower like this. Okay, and then another imaginary line of sine wave, another imaginary line of sine wave in the negative side. Then I can draw the waveform like this. Remember in the exam, don't waste your time using a ruler. Okay, doesn't matter whether your drawing is not good, it's okay, no problem. Even my drawing is not good, you see. If you're good in drawing, that means your sine wave would be much better than mine. Something like this, okay? So when you draw, of course, you have to label VC and, V versus T, and then you have to label the Vmax and also the minus Vmax. And also the Vmin. Okay, the Vmin is over here. Vmin. And also the minus Vmin. So how to calculate Vmax and Vmin? So it is stated over here. Vmax is Vc plus Vm. Okay. Why is it complicated like this? So Vmax is equal to Vc plus Vm. Okay. So Vc is 8.6313 plus Vm that we already found is 7.07. Okay. So plus 7.07. So you're gonna get 15 point, yeah, 8.6313 plus 7.07. So 15.7013. Okay. Vmin is equal to Vc minus Vm. So this is 8.6313. Is it 6313, right? Yeah. 6313 minus 7.07. So you're going to get this equal to 8.6313 minus 7.07. So 1.5613 volt. So this is volt. Okay. So you just need to label over here. So this is 15.7013 volt. Okay. The other one here is 1.5613 in the graph. So this is negative 7013. This is negative 1.5613. Okay, that's it. You get the graph. Okay. Any question? Hello, can I get your response?
No, Doctor.
Okay. So if no questions, we can take the attendance and then we can dismiss. Okay. And I will share the slides and also the I will share the slides and also the recording video later. Okay. So please take your mobile phone and you can scan the attendance. Okay. I believe you can scan. Wait, So wait, I will open and you can scan and then see you next time. So QR code, let's wait for a while. It's a bit slow. So after you scan, you can dismiss, you can go to another class or you can rest, have a lunch and do any other activities. Where's the QR code? Let's wait for a while. Yeah, okay. Okay, see you again next time. Okay.
Thank you, Doctor.
Thank you,
Okay,
Doctor.
Thank you,
welcome.
Doctor.
Thank you, Doctor.
Okay, welcome.
Terima kasih, Doctor.
Okay, sama.
Thank you, Doctor.
Thank you, Doctor.
Okay, welcome. Have you scanned the attendance? Anybody has a problem to scan the attendance?
Thank you, Doctor.
Okay, welcome.
Doktor, saya tak dapat scan.
Nama siapa?
Indra Putra.
Indra Putra. Kenapa you tak dapat scan?
Saya scan dia tulis no data.
No data.
No data. Please check your
Okay, Indra
your
Putra.
registration.
Okay, saya dah klik Indra Putra.
Okay, thank you, Doktor.
Doktor, saya pun tak dapat scan, Doktor.
Nama siapa?
Nama Sanjeev.
Sanjeev. Okay, Sanjeev. Mana Nur Diana? Nur
Thank you,
Dania?
Doktor.
Okay, Sanjeev settle lah. Nur Diana tak
Okey,
ada?
Doktor, terima kasih.
Okay, sama. Where's the others? Nur Diana tak ada. Nurin Shuaida. Nurin dah. Nur Diana tak ada. So absent today, Nur Diana.
Terima kasih.
Okay, sama. Jumpa lagi.